Hello,
Hello.
Hello.
hello everyone, and this is the 106th episode of DevKami, and I'm Chilung.
And I am Tristan.
And I'm Swimming. And we have our usual guest here. He's not usual.
Yes.
He's not a guest anymore. He literally stays with us online virtually and occasionally join us. So there's Sean. And there's a good reason for it, but that comes later. Right? That comes later. Let's start with our usual thing before we go on. But before that, what's new happening to you guys? Anything interesting?
Nothing interesting for me. Last night I just went for a workshop. I had a headache, so I didn't really follow through. But that
Okay.
was quite an interesting workshop.
Yep. So how about the rest?
No, nothing
Nothing.
special going on.
The only
Stay
thing
at
So
home, don't
was
go out.
the only thing exciting
so
was visiting police stations today.
so my quick project, I finally start training, configure some training, but a few things still doesn't work on the computer because I'm using Ubuntu, so it's a bit experimental. Actually, it's a lot of the experimental, so I need to figure that out. Once I said, I hope to have something by Friday. I doubt it. Maybe it's more likely on Monday. Let's see how it
Mhm.
goes. So let's start with our usual thing, which is our meetups. So on Saturday, we had an online study group by Women Who Code KL on AngularJS. Then on Tuesday, we had a Join Ruby KL and Penang meetup. And yeah, so if you're, I think this about the two events that are happening next week. So let's go through our.
So if you want to know, if you want the links, go to devkami.com/meetups or go to devkami.com, go to meetups, and
Yeah,
click on
all the
that.
links, all the links is here.
Yeah.
So just click on the links and you should be on your way lah, as long as space and all that. So let's move on to our bus corner. The first one is engineer introduce a service mesh. The interesting thing for me is goodness. The interesting thing to me is actually what take Nginx so long, because we effectively use Nginx for this kind of thing. Close, but not the full package. But that's what we do lah. So what you guys think?
What does it do that's different from normal load balancing?
I it's more like service integration for microservices. So they do tracing, Grafana, and all that. Then they do the traffic management and all that lah. So it's do a bit more than just pure load balancing. Very interesting for microservices. A bit overkill if you don't use it, but has a very cool idea behind the scene. So I just like the idea. So that's that lah. There is multiple service mesh in the microservice world. You should explore that. I'm not a microservice practitioner, so I can't comment that much lah. But it's interesting to me because Nginx have been. It's natural for Nginx to do that, but seems it doesn't lah. So if nothing, we got quite a lot, so I'm going to move on relatively fast. This cross-sec is actually something like fail to ban. We actually the project attempt to crowdsource IPs and all that. It's similar to fail to ban, right? But it's more collaborative and modernized because fail to ban is actually a bit ad hoc. It's one configuration file which you just commit on your version control system and all that. So CrowdSec is a bit more modern, I believe. So they're trying to do a bit more thing. Same idea, but it's more than just configuration file.
So
So,
how
yeah.
does this prevent like bad actors from polluting because this is a community thing, right? Like everyone, you're basically getting behavior from other people and applying it to your setup. So how does this prevent bad actors from polluting?
There is evaluation. There is actually evaluation. Then I don't know. to be honest. But I believe, unlike, because fail to ban have the same problem, right? It's an IP that is trust the community, which they decide to add or remove. So
Well, fail to ban is because you have to do it yourself, right? You have to like
they,
update the configuration for yourself. I'm expecting
correct.
CrowdSec is doing it like without like no hands, basically, like automatically doing it.
Yeah. I hope, because there is already agents and all that. So I assume that
Mm.
and also evaluation. I assume that they do a bit more than just fail to ban law.
Mm-hmm.
So that's what I think lah. Assisted setup, crowd and blah blah. There's reputation and behavior and automated. There's automation. So yeah. So that's that. Then the next one, let's keep it short one. This is actually traditionally when you do CUDA or open compute, you use C++ or C as a language. So this project was GPU attempt to actually write the use Rust as the program to actually write GPU code, so they can write shader and all that. It's called this HSSL. My bad, I'm wrong. It's a high level shading, like a shader language. So CUDA is all that. Traditionally you use that, but now you can, with this project you can use Rust lah. So So which is interesting, more language, better abstraction. Hopefully more interesting stuff coming in. So the next one is actually this from Tristan. Tristan have one, right?
Yeah, I already have one before. It's quite difficult to get hold of this. I mean, it's not. I mean, it's a watch, right?
Yeah.
But the thing is, because it runs an open source firmware, the thing is the SWD pins. So it runs an ARM processor, an NRF52840 from Nordic. The SWD pins are actually exposed at the back. So these pins are, you have your 5 volts, your clock and your IO and your ground. So they're all there. So it makes it very, very easy to upload your own firmware without having to open the watch. And so it retains its IP68 waterproof. You can take it in the shower or go swimming, and you still can reprogram the thing. So that's actually quite good. This is what the Pine Time should have been. But Pine Time is like running a very old version of, well, not really old, but relatively old version, the NRF52832. This is the NRF52840. So much better. It has GPS, has accelerometers, all of these things. So a very capable watch, and it's hackable. So it's actually quite good.
But is JavaScript.
No, it's open firmware, so you can run JavaScript. You can run, I mean, embed OS. You can run whatever. Does it say JavaScript there?
Bango.js.
Well, Bango.js is where's Bango.js? I mean, it can run Bango.js. That's one of the things it can run. So that's the thing. That's a great thing about open source, right? You can, it's just a microcontroller, so you can have it run whatever you want. Which is why the hackable watch is great. Like, imagine doing that to an Apple Watch. You're not able to run anything else other than Apple software there. Correct. So you don't really control the watch.
Yes. Very interesting project. If you get hold of it, I suggest you show us what you have done with it. I would love to see. In fact,
go to hackaday.io. In order for this to actually get like traction, go to there, like or follow the project, and then get updated there, because that's where things are happening. So there's already like some firmware there. I think some people, I'm in part of this Discord that actually does some Arduino framework stuff on the watch. So they've already reverse engineered the LCD, all of the things. I mean, it's just SPI and I2C. You just need to know the data sheets, right? So they're actually asking if anyone has data sheets for any of them, then they will be able to reverse engineer more and then add more to the firmware.
Right. So interesting stuff. I would love to try it for hacking purposes. And let's move on, because we only have 5 minutes. So when Cloudflare actually had their announcement on their birthday week, one of the things that announced is actually gRPC support. So so it's not just use HTTP, but also use gRPC. So you can use gRPC on your Cloudflare service to get all the performance and all that lah. So this, if you go to the site, which is actually you can go see on our blog, you see the technical detail of what they try to do and all that. Very interesting stuff. So next one is we use Azure. There is a new roadmap on all the product. But I think let's move on because the next one is more interesting. Because YouTube DL takedown is very troublesome. It's a DMCA takedown. I think here's the thing.
What do you mean by DMCA takedown? What's special about DMCA?
So DMCA is the Digital Millennium Copyright Act. So it's a very overarching law in the US, which actually in the name of protecting copyrights, allowing copyright holder to do a very wide takedown. So they actually allow company to it doesn't just allow company to add DRM on a song on their device, but they also enable make it illegal to break this DRM if you want to make a copy of a song or whatnot for whatever reason. So in this case, the DMCA takedown is actually very wide. It's actually a very blunt tools that is overly broad. So because there is often good reason for you to break. So one of the reasons that I want to add DRM is so that they want to prevent copying of songs and media. But in the day where we actually bought DVD and all that, DVD rots, right? So CD rots. So and they make it illegal, quote unquote illegal, for you to actually make a copy of your song, even though you already bought it. I think this is considered fair use exception now, and they keep when they have it is very problematic, and it turns out they also make it hard for people to do things like breaking a phone, because your phone had a lock and that is considered as a DRM devices, and breaking it is illegal. So it's a bit too wide. And in this case, they take down YouTube DL, which is actually a tool to download media from YouTube. So in this case, there's good reason to have that. We use this on our channel so that we can actually convert the video into audio before we upload it to be used by Spotify. The script is currently there, not for this reason, it's for laziness, but there is very good reason to have these tools for this. So these tools have multiple use and not just for quote unquote pirating the song, right? So yeah. So this actually allows a lot of developers and even CEO of GitHub are involved. So yeah, I think this is interesting how to see it, but I think this is taking down of YouTube DL is uncalled for. And yeah, it shows the problem of DMCA law. So anything you want to add to this thing?
No, do you use YouTube DL?
I thought we use it, and we use that to actually make a copy of our audio.
For a podcast, right?
Yeah.
Sean?
So
I think the issue is because there are actually a lot of legitimate users for this tool.
correct.
Mhm.
Now people use it legally, perfectly legally, and
Yeah, correct. Which is our problem. Correct. Because the complaint is for one song, and they use this song to actually goes against everyone. So I say it's a very wide tool. It used to be a bit worse. They used to make it illegal to break your computer and all that. it's a bit easier.
I think the issue in the DMCA takedown notice is that it's like using a sledgehammer to swat a fly.
Correct.
It's a super broad thing that just whack everybody.
Correct. I'm going to move on really fast because it's my favorite topic and all that. The next one is AWS now have open public preview of telemetry-based distro to be used for open telemetry to measure your services and all that. This is actually a very hot stuff for you to actually measure performance of your software, your errors and all that. With AWS having this to build into the distro, it make it for us to have all these best practices to be built into whatever we set up. So yeah. The next one is GPT-3. They use GPT-3 in chatbot experiment, then it backfires in short. This is a reminder that AI, quote unquote again, is not ready, it's not pixie dust, it's something that we need to test, we need to evaluate, and often you need to tune, because this is not something that you sprinkle on your cake and it will automatically taste good. So interesting experiment, and now you know. So which is why I'm a bit skeptical about what GPT-3 can do. You need to be very careful about it, and you need to really test it. Then move on, because do that. IEO, this is for initial exchange offering and digital asset custody. This is actually mostly for cryptocurrency. So SC of Malaysia now have rules for this. So it make it now we have rules if you're doing cryptocurrency trading and all that. So yeah, I still think cryptocurrency is a Ponzi scheme thing, but that's just me. And final one. This is interesting for me because recently I'm learning deep learning. So these are GUI tools for you to work on deep learning. I find this interesting because most of the model is already available, and if you make it easy for people to access and build tools for it, I think it's a good thing. So if you're interested in these tools, go to our link and you'll definitely see it. And I think that's all for Buzz Corner. And I don't think I'm going to add anything because, we're kind of short of time. So let's start with what we have shown here today. The short answer is, oh my goodness, you see all my tab. Give me a moment. Okay, so recently, Tristan actually bought from his Element 14, we have been saying multiple times, he actually got an evaluation kit for FPGA service, and here on DevKami channel, it's actually he actually had a few interesting questions and also a few interesting discoveries. So let's start with what you think about your little adventure and misadventure about FPGA first, Tristan.
Yep. Sorry, wait. I'm changing my, what do you call this? Bluetooth. I can't hear anything right now.
Yeah. So one of the things about FPGA, what is FPGA? Also very interesting around is because recently AMD actually have they bought Xilinx?
Approved. I mean,
they can buy, but
shareholders' approvals.
Yeah. So AMD want to buy Xilinx. Xilinx is a provider.
Xilinx. I think they pronounce it Xilinx.
So they are creator of FPGA tools, chips and all that. And it's actually very commonly used for people to actually work on this. So FPGA have been on hardware for reasonably niche reason. It's not common, right? It's not a 100% common thing, but it's beginning to. At one time, it's very commonly seen on the cryptocurrency side to start building specialized hardware to mine cryptocurrency. Recently, there is talk to actually use this to accelerate certain type of computational computation, because you can actually have specialized hardware. So yeah, so FPGA as a tool is very interesting. I do not know how big it will go, but AMD want to buy this for their compute user, meaning they want to integrate to their data center. So which to me is interesting. I do not know how it will go in the future, but yeah. But for now, let's start with Tristan's misadventure or adventure. I do not know what to say.
I don't know. I haven't really. Well, I think the biggest questions I had in the beginning was the difference between FPGAs and microcontrollers, and now ASICs as well. Like now ASIC is actually like something somewhere in the middle of the mix, where it's an application-specific IC, and which is something like what you would use an FPGA if you froze an FPGA, and that's what you sell basically into things. Like a microcontroller is like a very narrow subset that can only do single processes, like single tasks one at a time. And then you, in order to do like real time, you have like interrupts, which basically like stop the microcontroller from doing something and then doing something else. So basically something like that, and it's a different way of thinking. So that's why I was asking on the
So
engineers my Slack on about all of these things.
And I think let's start with one at the beginning. Let's start with. So the reason we have Sean is because he's a literal expert, so we can have this. So let's start with some explainer. So what is FPGA? Then what is ASIC? Then what other keyword you say just now? Let's start with these two. Then we continue from there.
Yeah, and then microcontroller. How is it different from a microcontroller?
Yeah.
Okay. So I think I will start by saying that first of all, FPGAs are not something new. I have personally been using them for 20 years already. Okay, so it has been around for super long time. Just like you said, recently it's more popular in the consumer space because of cryptocurrency mining. Right? Before that, the only people who use it are probably people like me, people who are actually working in that particular space. Right? But what's an FPGA? So one way to visualize an FPGA, okay, what does it stand for first? FPGA actually stands for Field Programmable Gate Array. So as its name suggests to you, you can already roughly tell, you can roughly visualize that, okay, this is a device that has a lot of gates in it, digital logic gates in it. So that's the good way to visualize it. Now, what can you do with digital logic gates? Anyone who's an electronics engineering student can straight away tell you that if you have digital logic gates, you can literally build anything you want, right? If you have logic gates, you can do logic. But besides logic, you can combine logic gates in certain ways, and then you get something like a flip-flop. Right?
So, logic gate, you mean like the AND, the OR, the NAND, and XOR, all of these things. The things that we software developers take for granted are the building blocks of the FPGA.
They are not actually the building blocks of the FPGA, but it's a good way to abstract it and visualize it. All right, the actual building blocks of FPGAs are actually SRAM. All right, but it's a good way to visualize it if you are thinking of applications. So you imagine you have a whole device. Let's say you buy a chip. You have one device, like for example the chip. A typical FPGA, for example, a Spartan 6 or a Spartan 7 or RT like you have, will probably have like a few 100,000 digital gates inside it.
This one has apparently 800,000.
Yeah, so
almost a million.
That is an entry-level FPGA. Entry level. If you go to the advanced FPGAs, you're talking a lot more than that. Yeah. Okay. So you imagine you have a device with like 800,000 logic gates in there. So what can you do with that? The answer is pretty much anything. Right? You can use digital logic gates to build logic. Like I said, you can use digital logic gates to build flip-flops. And flip-flops are basically memory storage devices. They can store state, ones or zeros. Right? And then from there, you can then build other things. So in the end, you can build memory, you can build adders, you can build multipliers, shifters. You can build everything in hardware.
So in short, you can it's a way for you to design and build a CPU as well.
If you want to build a CPU, yes. If you want to build a CPU, yes. But it's not the only thing you can build with FPGA. You can also build a lot of other things that are non-CPUs as well.
Memories.
The main limitation of most FPGAs that you have today is that they are digital circuits. So what that means is you can imagine whatever designs you want as long as it is digital. There's no analog component in there. That's it. But you can pretty much build anything. So essentially, the sky is the limit, right? You want to build your own processor, you can build your own processor. You want to build your own graphics card, build your own graphics card. You want to build a simple UI for sending data back and forth serially, you can do that. You can do anything you want. So basically, the sky's the limit. It's up to your imagination, right? So that is the so-called FPGA device, and it's programmable. So you can just like software, you can write some code, synthesize it, chuck it in, run, test it out. If it doesn't work, modify, iterate lah. Change your code, synthesize it again, chuck in a new design, and then iterate until you get a design. Right?
So synthesize here is actually one of the words specific for. It's a term that commonly used in FPGA development. So what does that really mean? Is it like compile?
Okay, in a way, okay. Let me just simplify. Define what is synthesis first. So the official definition for synthesis basically is you are converting your the design entry, the design that you entered. So that is usually written in some sort of code. Let's say you write it in terms of Verilog or VHDL. Now, so when you've written your code, then you pump that code through a synthesis tool. This synthesis tool essentially takes your code and converts it into something that we call the target. Sorry, not target. The technology library. Or sorry, not technology library. The general technology. So essentially, what it does is it takes your code and turns it into the equivalent circuit. So you can have, for example, your code. If you, let's say, for example, you wrote A equals B plus C, example lah. Then when it sees that plus, the synthesis tool will know that, okay, this is a plus. I need to build an adder. So when the output that you get, you literally get a circuit for an adder. So in a way, what you said is true. You can sort of analogize it to, in software, is compilation. This compilation turns your source code, human readable source code, into basically at the end of the day binary lah, right? Machine readable code. So in a sense, you can also think of it that way. It's converting your source code, human readable source code, into circuitry, into hardware circuits.
Right.
All right. Now, just now to answer the question of where does FPGA fit in compared to ASICs and microcontrollers and all that. So what's the differences? The main difference is that in the case of a microcontroller, everything is fixed. The hardware is already fixed. The capabilities are fixed. The hardware is already built. Okay, so all you can innovate, or the only thing you can innovate or change on the microcontroller is the software. So that's the only thing you can do. You are limited because the hardware is fixed. Nothing you can do about it. Okay. Then, so what happens if you have some great idea that you want to build, but it's limited by the hardware that you have? Let's say the microcontroller that you have doesn't have certain capabilities to do this. So what can you do? One option is to actually go down the route of the FPGA, because in the FPGA, the hardware isn't even there. There's no hardware. You are literally going to design the hardware yourself. So one common example, like some of my clients, they have seen, they have this kind of problems. A lot of microcontrollers come with, for example, 3 I2C channels, right? So if let's say you only need 3 and 1 I2C channel, you can use to communicate with sensors. So let's say you have a small number of sensors, then 3 I2C channels is more than enough. So for most hobby projects, that's okay. But if let's say you're working on some industrial project, right? Then 3 I2C channels not enough. You've got like hundreds or thousands of sensors out there. So how? All right. So if you have a microcontroller, you're stuck. That's it lah. No more lah.
Yeah.
Right. That's it already. Yeah. So but with an FPGA, you want to have 100 I2C channel and 200 I2C channel and 1000 I2C channel, and the hardware is not fixed. So you just design in the I2C blocks, and then you can have 100 I2C channels, 200 I2C channels. Right?
I think that's the one that actually changed how I saw it when they talked about like all of these hardware, because they're just transistors in the end, right? Like the actual circuit is just transistor.
Basically.
Yeah, exactly. And when I realized that, now I can make like 1,000 as long as you have space inside the FPGA, right? And you're talking about space, not program memory. You're talking about space because they're actual small like logic gates inside. As long as you have space to create those circuits, then you can have them. And that I think that's the got it moment for me. And then, so this is actual hardware in this small tiny thing. It's real hardware that you're synthesizing, and which is why it's a synthesis of things.
And
sorry.
that is actually
Jamboree is talking about 800,000. I was just looking at the data sheet to correct. Mine is actually 50,000 because this is really entry level. Their ultra scale stuff is like on the millions
millions,
of
millions, yes.
millions.
So
Yeah,
your
sorry.
800,000 is actually okay, still like
Yeah.
normal lah. Like the ones that we use in my office is also a few hundred thousand,
Yeah.
so it's very normal. Okay? But yeah, exactly what you mentioned just now. And I just want to point out here that the biggest problem that a lot of people have when they start working with FPGAs is they bring in the baggage of software. You have to basically discard everything you think you know about software and computers, throw it all away. Because when you are working with an FPGA, like you said just now, Tristan, it is actually hardware. One big difference, for example, in software, everything is serial. Instructions are executed one at a time, right? So when most programmers, when they think, the way they think is serial. The way their mind works is serial. But with hardware, nothing is serial. Everything is parallel. The moment you have electricity, a wire going down, it touches two other wires. Those two other wires get the same current at the same time. It's not go one side and then go the other side. Right? It's literally at the same time. So most hardware designers, their brains are trained to think in parallel from day one. So that's why I said just now, the biggest problem if you're coming from a pure software side is, number one, the baggage. The baggage of how you think computers work or whatever, throw it away. Then if you think purely in terms of the hardware and how it works, then you open a whole new potential of what you can actually achieve with FPGAs. So as a result of this capability of doing everything parallelly, naturally it's parallel. You don't have to worry about multiplexer synchronizations, queues, whatever, things like that, because it's naturally parallel. As a result of that, FPGAs are usually more high performance than your CPU or even GPU. GPUs, we get high performance because they're parallel. They're basically massively parallel machines, right? But GPUs are still limited by the fact that their hardware is fixed, right? You have programmable shaders, yes, but your shaders are still fixed, right? With FPGAs, you can have everything parallel and you can program whatever you want in there. You can design whatever you want in there, as long as it fits within however many 100 gates or 100,000 gates or million gates or whatever that you have. So a bigger FPGA will be able to do more, right? Then the last thing that you mentioned was ASIC. Now ASIC, it stands for Application Specific Integrated Circuit, so Application Specific ICs. These are literally your chips, your custom chips. So for most common people, this is out of your reach, because this is literally you have to call up TSMC or call up a chip fab and ask them to actually manufacture chip for you. So for most of us out lah, right? They won't pick up your phone call unless you've got like hundreds of millions in the bank. Right? Okay, go away lah. But there is somewhere in between as well. There's actually another category of product that's somewhere between an FPGA as well as an ASIC. Now the thing about the FPGA is fully programmable. So for some people, that's also not very good. It's good for development, but when you ship the product to your customer, you sometimes want it to be fixed. Because with a fixed ASIC, you actually generally have higher levels of performance. Because in the way that the wiring and all that is done, for the FPGA, it's because it has to be programmable, so it has to be flexible. So in other words, you lose some performance in that sense. In the ASIC, it's hardware completely fixed, so you get the highest performance in the ASIC, but it's the most expensive, right? So there is another category of products somewhere in between. These are generally like what we call eASICs, in the sense that they are sort of like FPGAs, but quite often you can talk to the FPGA company like Xilinx or that they actually provide this kind of service where when they manufacture the FPGA, they don't finish the manufacturing. So they start building the FPGA, but the last couple of layers, they will take your design and put it in. So in a way, it is also fixed. It's hardwired, it's hard fixed. So it's not programmable, but it's not it doesn't cost as much as a full ASIC, which is like a few hundred millions. So so you talk to someone like Xilinx, they will customize the FPGA for you in a way. So it's a customized FPGA. That one, it doesn't cost as much. It's like in the range of few $100,000 US dollars and things like that. So not too
But-
expensive, plus even manageable.
What do you actually use it for? I mean, I know you already say about expanding I/O and all that. What else do you actually, in what situation where you would actually build? Okay, so the first question
Okay.
is, in what situation you want to use ASIC? And the second question after this is, why the interest of putting FPGAs into compute services or computation devices? So that's the two questions, right?
Okay, so I think first I answer the question of why we use FPGAs essentially.
Yeah.
What's the advantage that FPGA has over traditional thing? Okay, there are a few certain advantages. Number one, I already mentioned to you just now, in FPGA, everything is parallel.
Yeah.
Right, so you can have massively parallelized computation. So your performance for whatever algorithms or whatever you're building naturally becomes more performance. Right? You naturally get higher performance. Then as well as I/O as well, because FPGAs all have like huge number of I/O down there. Right, so if you like mentioned just now, like you want 100 I2C channels, okay, you need 200 pins. FPGA, no problem. 200 pins is a small FPGA, right? So you can definitely do that. So in any sort of, and not just number of I/O, high performance I/O as well. So like a lot of high performance hardware gear, like networking gear from Cisco, for example, they are all using FPGAs inside.
Right.
When you want to switch packets at high speed, it's the fastest way to switch a packet from one network port to the other network port is to literally wire the two of them together.
Right. Okay.
Compared to a normal router where you have a software that copies the data from one port and then pumps the data out to the other port, that's a lot slower. Literally wire them together and the electrical signal just goes from in straight away to the out. That is the fastest, right? So high performance you need that, right? But besides that, there is something in an FPGA that is very, very useful, a particular component in an FPGA that you don't find that in most other places. All of the modern FPGAs come with something called multi-port memory. Right? What is multi-port memory? Normal memory, you understand RAM, right? So you have RAM, you can read from it, and you can write to it, you can read from it. But you can only do it one at a time. You either write to it, or you read from it, because it has only got one port.
Right.
One bus to access the RAM. Now with FPGAs, it's pretty standard nowadays in FPGAs where they come with multi-port memory. So for example, so you have a dual port memory, two-port memory. So it's literally one piece of RAM that can be accessed concurrently from two different sides. So you can read and read, or you can read and write, or you can even write and write. So this gives a lot more power, in terms of computation. If you're doing algorithms, for example, you don't have to read, process, write, read, process, write. You can literally read and write and process at one go. One side read, one side write, one, and then processing in between, all at the same time. So again, it increases the performance. So that's why FPGA is usually found in all those kind of very high performance kind of applications. Okay, so which sort of answers your question just now as to what advantage would you have in like high performance. These are the kind of things.
I think another one for FPGA is in the name, like field programmable. So I was already thinking, like, let's say you have you sold a product with an FPGA to your client, and the client's vendor deprecated an I2C module and said, now we need SPI or something like that because that's the future. And oh, sure, okay, we'll just program your FPGA to have SPI hardware inside. It's the same pins, we'll just like change them to SPI, and then okay, now it's because apparently you have like standards of those pins, and then now you can use the new vendor or something without having to replace the machine or replace the whole thing. So it's field programmable in that way. The hardware changes based on how you program it.
But also another thing.
In fact, also, I just want to say, in fact, most companies use it the opposite way, i.e., you pay me more money and you get more features.
Right.
It's
so
not
it's like
it's
like feature, like you hold the feature hostage by like, oh, pay more money, okay, it's like what Tesla is doing. So this has been something in engineering for a long time, and people are like complaining just now. Oh, we'll activate your heated armrests for extra money.
Yeah,
Okay.
exactly. And literally just change the hard. So you change
Yeah.
the hardware, so it's physically there.
Mhm.
But because of this, so another application I think of right now is actually neural networks, because individual neural networks actually have very simple adders, right? And it's very simple to implement on the hardware. So what happened then is you can potentially implement a reasonable size one, maybe not a billion of those, but let's say a few hundred at one time, then you pretty much get a neural network that is fast enough on the hardware, and which is better than your GPU. I mean, not necessarily cheap, but it's definitely faster simply because it's an adder with wire that way. So yeah, which I can see how interesting. So okay, I can't tell. Shit, I had a question. I forgot about that. So
Just now I haven't finished. Answering the last part. So the ASIC part, like I was mentioning just now, most people will only go down that route when you have actually solidified your design. Because the ASIC again is not programmable already. ASIC is fixed hardware already. Right. So again, another application for FPGA is for prototyping. So before you, let's say, and they actually do this before Intel or Nvidia or whatever design a new graphics card, they will actually prototype the graphics card first inside an FPGA. And then they test it out, make sure it works. It will of course run at a slower speed than the final card, right? But clock speed is, so maybe you get lower frame rate instead of like 120 frames per second, you get like maybe 15 frames per second or something. But you can at least prototype it, test it out, and see that it functionally works before actually spending the hundreds of millions of dollars to actually tape out an ASIC. So that's another use case.
Wait, which actually I guess makes sense because you want the flexibility of reprogramming it instead of, because you have like what 5 nanometers, and to reconfigure that whole plant to rearrange the thing because you made a mistake is going to be very,
hundreds
very
of millions.
expensive. Yeah.
Hundreds of millions, right?
So yeah, I guess it makes sense for something to be programmable like that. Yeah. So you mean?
Okay, so how's the experience like for us to actually learn about FPGA for a hacker like us, right? So how's the experience like? That's one thing I'm interested. So I know you already say that you need to get rid of all the software concept, so you throw away. What else? And how do we start on working on this?
Okay, so as just like in software as well, there are all kinds of tools that we can use. Like Tristan has already experienced using some of the Xilinx tools.
Yep. It's this one.
And Xilinx, that's the board. Yeah, and it also comes with software as well, the Vivado suite and all that.
Mm-hmm.
Yeah,
it's free by the way for this one.
Free for only the low-end FPGAs. If you are going to use the ultra-scale one, it's not free anymore.
Yeah, that's where they make their money.
Yes, correct, exactly. So, but yeah, so it's free enough for the normal hobbyists to get into. And you can see that piece of software as well. It also caters to a wide range of users. If you are a power user, all right, you are a power user, then literally what you will end up doing is you will end up learning one of the languages that we can use. The most popular are Verilog and VHDL. Right, these are the two most popular ones. So you will pick one of these languages up, right? And once you learn this language, these are what we call HDLs. They are hardware description languages. So although they may look like computer programming code, they may look like C. Verilog looks a lot like C. VHDL looks a lot like Pascal, right? But they are not software programming code. They are actually language used to describe the hardware. Because in the past we were using circuits, we actually draw the circuits. So now we no longer draw circuits because the circuits are too complicated. In fact, imagine having 800,000 800,000 logic gates. You can't draw 800,000 logic gates. You die, right? So we use language to describe the nature of the hardware that we want. So that is the first thing that you need to learn, right? But once you learn that, then that's pretty much it. Because the synthesis, for example, will be handled by for example, the software tool, right? So just like compiling software, you hit a button, hit a button, it will compile it, right? So similarly, you hit a button, it will synthesize it. And then besides synthesizing, after that, it will bring it through additional steps, what we call place and route, to actually map the so-called circuit that was synthesized into the physical hardware that you have. So, and then once that is done, you will get a little firmware, a little bit stream at the end of firmware, a bit stream. We call it a bit stream. So that bit stream, literally, you can just download onto the board, and then you can see your LED blinking. Right? Your hello world. First thing you do is blink an LED. Right? So that's generally it. But of course, there's like I said, a range of tools. Nowadays, there are also a lot more automated or wizards or GUI-based tools to actually help you do the design. So instead of writing the Verilog code, you can also, for example, do drag and drop modules, or like Tristan was saying just now, there are some in the chat earlier that there are some tools using Vigilant PMods or whatever that.
Yeah. This is the PMod. It's sorry, I'll open it. It's hardware, so it's like a port, but they were using something called Vitis IDE, and it's which integrates with your Vivado, and they have something called Microblaze, which is synthesizing a CPU, and you program it with C. And I thought like that doesn't give me anything with FPGA, because I'm still programming a microcontroller here. So this is the PMod. It's IMU 9 degrees of freedom or something.
You are programming the code, but the physical connection part is in the FPGA.
Yeah.
Right. So that part is configurable, and that can be automated, like in the sense that you didn't really need to go and write the Verilog code to do the connection from the PMod into the FPGA. That part is automated. So in terms of tools, what I'm trying to get at is there's a wide range of tools, right? You can go the low-level hacker way, write everything yourself, or you could just use drag and drop blocks, and boom. Right,
I've also seen while I was researching the whole thing that there's a C to Verilog or C to HDL thing. So you actually write in C, but it transpiles it, I guess is the word. It changes it into actual hardware. So if you have your adder thing, you have a loop and you have an adder, it transforms to an equivalent circuit and then runs that as a bit stream. So I guess that's another way of doing it. I just haven't really.
There are a lot of other ways as well. Like for example, before we had all this cryptocurrency and stuff like that, a lot of other software tools like MATLAB, or even I can't remember what some of the other tools are. But basically, you've got some other tools like MATLAB or NILabVIEW or whatever that literally when you drag and drop and design all this code, or you write simple code in. I wanted to mention certain libraries. If I'm not mistaken, CUDA can do it as well. So if you are interested in doing machine learning, you can write code in like C and CUDA, and then it actually converts it to circuits that you can then download onto the FPGA and run it in. Like you mentioned, just doing neural networks in the FPGA instead of on the GPU. So there are a lot of tools out there. So there's a whole range. That's why I said. You can get very low level, working at the low level electronics, or you can just be very, very high level, use Simulink, drag a few blocks, and boom, hit a button and magically it goes into the FPGA.
Which reminds me of my computer architecture class when I do CS long time back. We almost think in blocks. We don't think in transistor level anyway. So we think in a block of adders, then combine. So it's like, we almost start from beginning. So we had an adder by this logic. From there, you add as a block, then you combine blocks and all that. So one question, never mind, that is what I remember in my computer architecture class. Fun time. So let's start with one question. What it is like to debug an FPGA?
Not as fun as debugging software.
Okay.
All right. Why? Because in software, it's a lot easier to debug. For example, you can pause the software. You can step through it one by one. Try pausing an electron. Right? You can't do that. All right. So not as fun in that sense. And also because the hardware engineers, we are not as focused on the software development. So in terms of the tools available, also they are not as well developed as the software tools. For example, software tools, you can even disassemble the code and then really, dig in and see what the hell is happening, right? But hardware tools are not as great, right? So we are still quite primitive. We are still quite primitive in the sense that there's still a lot of very old school way of doing stuff on the hardware to debug FPGAs. But that said, a lot of the techniques that we learn to do software debugging, a lot of them are probably transferable as well. Not just the techniques, but the skill set. In the sense that you also still need to have a good idea of where to start. Because if you have a problem, you have no idea where to start, then that's it. You just give up, right? So you still need to have a good idea of where to start. Then, of course, when you have a good idea of where to start, there are things that you can do. For example, you can isolate just that one module or just that one function. Just like software, you isolate one function and you test that function, for example. So in hardware also you can do that. You just isolate that one module and then test that one module. Your unit testing, integration testing, system level testing, all of that, those skills that we've learned can still be transferable. I'm just saying the actual doing it is going to be more painful. That's all.
Yeah.
So during the workshop, there was a lot of talk about like people who have done FPGAs trying to reduce state machines over and over. And I commented like, why are state machines like war stories for FPGAs? Is that because of the debugging thing?
Because essentially, if you think about it, every single thing that we are designing is basically a state machine. Even the CPU is basically a state machine.
Yeah.
Right. So state machines are basically gonna be the main thing that you'll be seeing every day, right? So you'll be spending your time debugging state machines all the time. And state machine, when you're writing your Verilog code, it's very easy to get wrong. It's very easy to make mistakes in state machines, right? So for example, if you just in a normal switch case, all right, if you're writing software, you can just write your switch case and then without caring about anything, just write the switch case, right? Designing a state machine, for example, in Verilog, also we often use a switch case, right? But when you write your switch case in Verilog, if you make certain mistakes, like let's say for example, your input variable is only 4 bits, and if you're not careful, you have cases that are 5 bits or 3 bits, even 3 bits, it can mess things up. And this kind of thing sometimes is like silent errors, because the synthesis tool probably just shoots up a warning, which we all ignore, right? And then you just run it to the end and you'll be wondering, why is this state machine not working, right? Because, you just made a small mistake by missing out the width, whether it was 3 bits or 4 bits, or maybe 5 bits or whatever, right? You just missed it out a little bit, the whole thing was messed up already, right? So it can be a bit more troublesome. And if we are not careful, the way we write the state machine in the switch case, if we don't write it correctly, it doesn't even get turned into a state machine. It gets turned into some huge mess of asynchronous circuits, logic gates. So it can even be that way.
And
So
you
it's
don't even
very,
know,
very
like
troublesome.
the behavior is basically undefined because you don't know what the hell this thing is doing.
Because it's an asynchronous circuit, it's completely boom. You have no idea what's going to happen. So it's a bit more. You have to be a bit more careful when you write a switch case in Verilog than you need to if you're writing, let's say, in C. So common mistakes.
So, Swimming, should we go to the latest news about FPGA world?
Yeah, what's the latest
is-
news? Is it?
AMD buys Xilinx for 35 billion.
Yeah. I already asked about that, but what you think is the reason, though? I know you already said that networking is definitely helpful because Cisco switch literally just connect the circuit and do your switching instead of doing software magic thingy. So, in fact, the more interesting and the reason why we raised that also is because AMD is buying Xilinx so that they can put it into their data center business, which is interesting to me, but I don't have any idea why. Why would they want that?
Okay.
Well, when
Let me
Intel
just postulate lah. Let me just guess lah. We obviously none of us will know lah. We are not the CEO of AMD. We have no idea what they want to do, right?
Correct.
Putting it in the data center, for example, can be as simple as, for example, now they can sell you a single motherboard. Example, But this motherboard, you can use it for a network storage, because you can use it as a network storage. They just need to program the FPGA, put in a lot of SATA controllers, for example, or NVMe controllers or whatever, and boom, you can use that motherboard to store massive number of storage. Huh? All right. Then the same motherboard can also be used to, let's say you want to do cloud computing, right? Not storage. You want to do more CPUs or you want to do more memory, right? They can just instantly put in 100 memory channels in there, for example.
So it's
You're
fast
talking
enough
about
for the-
economies of scale in this case, like the same motherboard, multiple uses.
You can use it for network storage. You can use it for cloud server. You can use it for networking gear. Networking gear, the same FPGA now gets programmed with a switch fabric,
Mhm.
right? So then you just same motherboard again, same everything exactly the same. You don't need to have different ones.
Mhm.
But does it mean that, so let's say, I know this is a bit weird, but so let's say there's a new type of connectivity. So for example, we move, for some reason, we move on from PCIe. So does it mean that as long as we can provide the connector, we can literally program the hardware without, and only provide the connection point?
The connector is
like
cheap. It's just plastic.
Right.
The
Yeah.
connector is just plastic. It's cheap. The circuitry, what is normally if you buy a motherboard is the chipset lah.
Yep.
Right, the chipset, right? That's where everything is connected to, right? Your SATA, your USB, everything is connected there. Yeah, so that chipset, you can literally have an empty chipset blank going into reach the data center, and then the data center can then decide what they want to do with it,
Right.
and then program the FPGA to do it.
Okay. So
An example.
okay. Yeah.
So, well, looking into the future, so because now we're just so FPGAs, you have a fabric of like logic gates and you synthesize things, right? What if you can have like nano machines, and will that be something in the future? Well, it's 3D because right now we have like a chip.
My opinion on that.
What's a nano machine?
Well, let's just say it's like a logic gate that can move by itself. So it's self-propelled logic gate
okay.
that can connect to each. Yeah.
Yeah. A
What-
MEMS
what
is
do you
already
think?
possible,
Mm-hmm.
Yeah,
but not
I mean, with
universal
MEMS,
assembler.
sorry.
Not universal assembler. Universal nano assemblers is impossible.
You will be surprised.
No,
They have already
it's a-
managed to build MEMS robotic arms.
Yeah. You can build an arm. You can bake proteins and all that, right? But it's not the Drexler style. You know Eric Drexler. He's one of the first. He's the people that comes up with the universal nano machine. So the thing is, you cannot assemble everything, but you can assemble Lego like molecules. That's the interesting part. So
But
yeah, that'll be
that's where
interesting.
everything starts, right? When you start miniaturizing things, you had vacuum tubes, and then you had like transistors, TO 22 or something, and then now it becomes small, and now you have 5 nanometers, and you
Yeah.
have lots of things happening. And it's the same thing with these self-propelled. I'll call it self-propelled logic gates. Like as they go smaller and smaller, you have your building blocks, and those building blocks become building blocks of something else.
Yeah.
Until you
use
can get an
you use the arms to build smaller arms, and those smaller arms to build even smaller arms, and
yeah, and
until
then
you
it
can
gains
start manipulating at
sentience.
the atomic level.
Yes.
So
And
that's
you
the
have
good
like
side,
a
right? Yeah. But currently, the technology for that is called MEMS, but a lot of scientists working on biology. So the MEMS, they actually in use in one of the more famous places. It is in use in your ink cartridges. Your printer ink cartridges, you know how they actually spread those things out? Those are MEMS. It's a micro machines on it. So your other place for micro machines is your your microphone is a micro machine nowadays. Not this one, not this one. Something like your Bluetooth, very likely are micro machines.
One very common use case for MEMS machines nowadays is actually to design electronic oscillators. So all the oscillators you have on circuits, all the clocks, especially the super high-speed clocks nowadays, it's actually a physical vibration. It's no longer an electronic clock. Really. It's a physical.
Also, your crystals, they're not really crystals, but if you call it MEMS crystal, it's an actual thing. Oh,
In your smartphones, MEMS.
Yes.
It's a mechanical vibration.
So your accelerometers, your microphones, your crystal, definitely. So those are MEMS machines. So, but MEMS is interesting. I would love to say. There is one time that I want to. There is one time that I want to do nanotechnology.
Oh.
It's very interesting to me. But there is this scientist. He's a Nobel Prize winner that said there's a fat finger problem, so you cannot assemble atoms, but you can definitely do molecules. So that's why it's interesting.
So let's go through some of the questions on the comments.
Yeah. Okay, so
Google-
it's what? Now let's start from you first.
Yeah, sorry. No, yeah. So I was talking about Sean on DevKami number 107 should walk us through his books in the bookshelves behind, because you seem to be. I should change my background to like nice books as well.
Yeah.
Like in general, what do you have? You also have
okay.
like swimming also has.
Okay, so generally, this part is fiction.
Uh-huh.
This part is fiction. This part are engineering books. My favorite topic is microprocessors. So this row up here is mostly microprocessor manuals, including some really, really old and out of print stuff.
Whoa. We can raid your bookshelf and sell some of them for like expensive.
Ooh, I know Transputer. That's the Linus first company, right? Linus used to work there.
No, that's Transmeta.
Oh,
This
that's
Transputer is the first parallel processing computer built. Super old. You can no longer find it nowadays. But yeah, so this is the data sheet basically. The data. Yeah, so this is a museum piece. But yeah, so these are my engineering books. Then over that side I have my law books. And over there is all my Blu-rays. These are all actually Blu-rays.
legal, huh?
These are not. Yeah.
So Kyril was asking if you can have like a program an AV1 decoder. I don't know what an AV1 decoder
Those
is.
kinds of things are basically like final year projects and master's level projects basically. For FPGA, like to encode or decode video or audio. Those are very standard kind of projects.
Okay.
I mean, it's the thing is, you can decode those like with codecs, right? But then they all had to be done in hardware anyway for like your TVs or your like set-top box devices. No?
The main advantage for doing it in an FPGA, if let's say you're talking about let's say audio codec or video codec, would be the latency. If you do it in software, you will always have a significant latency from the signal coming in and then before the signal getting out, right? If you do the decoding entirely in hardware, you can squish the latency down.
Because based on the frequency, then you can just filter it out all in parallel for across all the spectrum, right?
Yeah, everything can
for
be done
real-time applications.
Essentially, instant audio processing. Like because that's what Kyril likes to do, right? Audio.
So
Instant.
the next question is: want to be famous? Yes, but not through you, stupid spammer.
We're having spam bots on Twitch, so
We are famous now.
it's cool.
I think that's about it, though.
Those are most of our questions. Some of them we've already answered.
Yeah.
Some of them about YouTube with late notifications, but I guess that's fine.
I think that's about it.
So how can anyone reach you if you're willing to be consulted on something? Do you have like a website?
Easiest way is probably to find me on Twitter. Right, so on Twitter I'm at Cybrion. Let me just change my name. Right, so you guys can find me if you want to. Yeah, that's me. Alright, so
you can
that's
tweet
the
at him.
easiest way to get me.
You have a final year project on audio video codecs, tweet at him, and he'll tell you to read a book or something.
Only tweet stuff at me that G untuk tontonan umum ya G.
Rated
No adult rated stuff yeah.
Okay. And that's it. Thanks for listening. It's really enlightening. So yeah, and just for transparency, the Citron guys, I'm still getting confirmation. It might not be next week, so let's see how it goes. So
Yeah.
I try to get more hardware hacking because I just remember that we had a company called Myduino, not as well known, but have been working on custom hardware. So I think that would be very interesting as well. So they're focusing on something more higher level, not a microprocessor, circuits and all that, and also do the Arduino class. So I'm going to ask them soon. Transparency so there'll be more hardware hacking related talks soon lah. So that's one thing. So yeah, I think that's about it. So shall we say goodbye? Goodbye.
Yes. Goodbye.
Yeah, ta-ta.
See you again.